Our next speaker is Massimo Stiavelli, and he'll be talking about JWST.
Hello. It's a pleasure to be here. I want to thank everyone who managed to remain here until the afternoon of the last day. So I'll be saying a few things about JWST. First, I'll describe the instrument capabilities, and then I'll, the project status, say a few things about what JWST can do for this field. This is partly inspired, things that I had written before coming here, and then I tweaked the slides on the basis of the presentations in the first 4 days. Then I'll say a few things, if there is time, about the timeline. So JWST has wavelength coverage from 0.7 to 28 microns, both imaging and spectroscopy. It has 4 instruments: NearCam, which is a US instrument; NearIS, which is a Canadian contribution, is a near-infrared slitless spectrograph. MIRI is a joint US-European instrument. It's the mid-infrared instrument, does both imaging and spectroscopy, as you see. NearSpec is the European, most European instrument, is the ESA-provided near-infrared spectrograph. I'm saying mostly because it has the slit selection and the detectors are US-provided. Again, NearIS can do imaging, spectroscopy, and NearCam can do slitless spectroscopy. So I'll try to go quickly through the instruments. NearCam is 2 cameras. Each has a field of view of roughly 4 square arc minutes. And each of them has a dichroic, so with every pointing, you get a long wavelength and a short wavelength spectrum. So you get essentially 2 wavelengths over 8 square arc minutes for each pointing. The sensitivity, as you can see, goes down to about 10 nanometers, nanojansky, for the broadband filters. And it does have coronography as well. And it's the short wavelength channel is diffraction limited. It samples the PSF at 2 microns, and the long wavelength channel samples it at 4 microns. The near-infrared spectrometer is a pretty fancy instrument. In order to do multi-object spectroscopy in space with slits, you need a slit selection mechanism that can work on a spacecraft and doesn't require cutting, little metal plates with a laser. And so the solution used for NearSpec is to use a microshutter array, which is a micromechanical device. I'll show you something about that, but first I'll say that the instrument covers essentially from 0.6 to 5 microns. It has 3 resolutions, 100, 1,000, and just below 3,000. The little slits are around 0.2 by 0.5 arc seconds, but there are also some fixed slits, and there is a 3 by 3 arc seconds integral field unit. This is a picture of what you can do with a microshutter array. This has been obtained by simply turning on and off some of the microshutters. So obviously it's quite flexible, and the little dark dots are microshutters that are failed closed, so you don't get light through. This is a picture of what one of those microshutters looks like, taken on a scanning electron microscope. Compared to the size of human hair. So here you see more of those little cells. Each of these microshutters actually, when it's actuated, flips by 90 degrees and then is captured on the vertical wall. So this thing flips on the side and is captured electrostatically on the wall. For things at this size, a 90-degree deformation is actually in the elastic regime. So when you let it go, it will will flip back to the normal state. So that's how you define the slits for NearSpec. The mid-infrared instrument, as I said, does imaging and spectroscopy. It has a smaller field of view. It has coronagraphs. And it has a single slit at low resolution, and it has integral field units at high resolution. And finally, the NearInfrared instrument, the Canadian instrument. The Canadian also provide the guider, by the way, for JWST, but their scientific instrument can do wide field slitless spectroscopy over a 2x2 arc-minute field of view, and it has a mode to do exoplanet spectroscopy at R of 700 for essentially a single object mode. It has also an aperture mask interferometer, which is a relatively new technique, certainly in space, where you trade some of your collecting area for sharper look at objects. So this is a summary of the sensitivity. I won't spend too much on this. It's an imaging, as I mentioned, with NearCam, is around 10 nanojansky, and it is better than 100 nanojansky in spectroscopy at R100. And of course, so what's the status of JWST? Well, over the spring, the OTE was completed. This is a picture of the 18 segments. These are beryllium segments coated in gold. You see the secondary mirror folded. The tertiary mirror and the fast steering mirror are in this box. So that was one of the milestones that had to be completed. This is another picture of JWST standing up in Building 29 at Goddard, the large clean room. And you can see here in reflection that the mirror is actually a mirror, in case you had any doubt. And it's, apparently, I heard the story that somebody working on ground-based telescopes went to see it and said, yeah, that's pretty small. Well, it depends. Compared to a 30-meter, yes, it's pretty small. But for being in space, it's not that small. As this is being assembled at Goddard, and testing is going on at Johnson with a demonstrator unit. It's essentially the back plane of the sun shield, except the wings, with two spare primary mirror segments. And this is used to test that the hardware supporting the test at Johnson is okay. And by the way, this is the door that lets the whole thing go in. It's a pretty gigantic structure. This is the instrument module that has been installed already in the back of the optics. The thing you see on the side is NearSpec, which is perhaps the largest of the instrument in terms of volume. This has completed 3 thermal vacuum tests at Goddard, and so it's ready to, and it has been installed on the back of the telescope. A large component of the telescope is the sun shield. This is a demonstration an engineering unit with the 5 layers fully deployed. It's been used for a lot of deployment tests to make sure that everything is okay and tweaking the design. And of course, the flight version that is being built now will also be tested. And finally, we have completed the Flight Operations Center in Baltimore at the Space Telescope. Unlike for Hubble, the JWST is actually operated by us, starting from a couple of minutes after launch. And so all the deployments will be controlled from here. Launch is on an Ariane 5 out of French Guiana, and out of reasons of time, I didn't include the deployment video, but you can find it on YouTube. I would recommend you to look at it. Mars Curiosity developed this video, what was the 7 minutes of terror. In our case, is the 7 weeks of angst, but it's pretty interesting to watch. So what can we do? So I try to think of what is the question that or one question that you might want to answer. And I thought that something that probably we should try to answer is, can we detect POP3s and prove that they are primordial? So something that you can argue in, and believe it, that it's an object with primordial chemical composition. And other people have mentioned this as a problem at the conference, like Jared. And as a sub-questions, of course, we can test our models, we can compare cosmological models and so on. But it would be interesting to be able to say, yeah, our view of how POP3 stars form is correct. And so how do you do that? Well, you can look at pair instability supernovae. They are bright and rare. One of the questions, and I'll say a few things about each of these later, but one of my questions on this particular one is, how do you know if you see one that it's a pair instability supernova from a POP3 star? Because now people start to doubt whether zero metallicity is really needed to get a pair instability supernova. So that would be a drag, because you see one and you don't know if it's really a POP3. And so are there spectral signatures that we could catch with JWST that would be different from another supernova? Or how do we tell? Would the light curve be enough? The other one is POP3 clusters or dwarf galaxies. Do they really exist? Do POP3s form just isolated or a pair? Or is there a chance that we could form sufficient number to detect them, either directly or through lensing, maybe? Another one is pair instability abundance patterns. People are obviously addressing this locally, and there have been talks about it. Is there anything useful we could do at IZ? A problem here is, do we have enough spectral resolution we do anything useful on this with JWST? And then black holes, there are different formation scenarios. Can we tell them apart with JWST? So let me start with some notional, to give you an idea of the capabilities. I decided to imagine 3 surveys that are the corresponding HST surveys with a J in front. So a J Cosmos, a 2-square-degree survey done with JWST, and say 2 epochs, 2 filters, and would go around AB 27.5. A J Goods, 400 hours for a medium deep survey, 2 fields with 6 filters, 360 square arc minute to AB 28.9. And then a J UDF, 400 hours deep, 1 field, 6 filters, 8 square arc minute to AB 30.5. So let's imagine that somebody will do this. What could we get with that? Or how far would we go for the 4 areas? So for the JWST and early supernovae topic, POP3s are probably very rare. So I suspect that even that J Cosmos survey wouldn't bring us very far. It sure would be nice to have W first while JWST is still operating, to follow up, but object detected by W first. The other issue, of course, is that the time curve is slowly varying, especially after you multiply time by 1 plus z to get to the observer frame. So it would certainly be very nice if some other facility found them for us so that we could follow them up. There's been a poster where they've discussed possible rates of pair instability supernovae. The red line is the type of rates that would give us 1 object in our Cosmos survey. So that's not very good statistics, but it's better than 0 objects. So you would want to be somewhat higher than these curves. So in some of these models, maybe if you have this rate over a delta z of 10, you could perhaps do something, but it's certainly challenging. In terms of luminosities at the peak, it should not be a problem for JWST. The same poster discusses what you could do to discriminate cold dark matter from warm dark matter. And again, in order to tell the blue from the red from the black line, you would need several of these objects. So I'm skeptical that you could go very far with the J cosmos. The consideration, though, is that you could do other epochs. Not too many, but a few. After you started 2 epochs, every 300 hours, you would get another epoch. So you have like the first 300 hours for the 0 epoch are an investment, and they are lost. But after that, every 300, you get another epoch. So you know, if you bring the program from 600 to 900 hours, actually you double the number of objects you can see. Of course, there are not so many useful epochs because of the JWST lifetime is finite, and if you want to have epochs separated by a few years, you can only get so many. So that's a problem with these very high redshift plateau supernovae. So for the first stars, direct detection is hopeless. You would need extraordinarily high lensing amplification to be able to see one of these objects. And there are papers that study what kind of amplifications you could get. Of course, if POP3s were very common, you would have a better chance that one of them is just in the right place near acoustics that gets a high amplification. But I'm somewhat skeptical that this is going to happen. Once you go to bigger objects, we consider, kind of little bigger objects could be detected with some more reasonable lensing if you have enough of them, and this has been considered by others. And it seems possible that JWST will see objects up to redshift 15. One comment that sometimes is made is, I'll start from here, is, tau is going down, that's bad news for JWST. I think JWST doesn't care about tau. The galaxies that we see will continue at some higher redshift. I don't think there will be, here's the end of the universe. And in fact, the high values of tau were a problem to explain. The galaxies do what they do, and then you have to see what tau you get from that. But I guess what I'm trying to say is that the halos are there, they will be populated by some stars, not a lot, and JWST will see. This is an estimate we made long ago, just doing something very crude. Dark halo statistics, some simple recipe to turn halos into stars with some efficiency. And we were kind of guessing that you would have about 10 galaxies per NearCam field, a redshift 10, maybe 1 or 2, a redshift 12, and a 10th. So 1 galaxy every 10 NearCam fields, a redshift 14. These are all more sophisticated studies, but the conclusions are not very different. Here, for instance, they consider three different models, normal, peak, and void. And the triangles, I think, here are the bright JWST objects, and the square are the deep field JWST objects. And you can see an handful, even a 15 in the rare peak. And this is the same study for the three, and this is the JWST detection line. And others have found somewhat similar results. We get above the deep field line around redshift 12 to 14. So we'll see galaxies. Whether or not these are primordial, that's a different issue. As Volker pointed out, there is the high likelihood that the first galaxies we see are already metal enriched, so they won't be POP3 objects. So the first black holes, at least judging on this conference, it seems that consensus is the redshift 6 QSOs are formed by direct collapse. We heard from Volker, we heard from Priya, and from others. There was a little bit of a scary talk suggesting the Lyman-Werner escape could be very low. If that's the case, it might be hard to fry H2, especially because it would be even lower on a big galaxy. But it's worth looking at it. Also, I don't see a lot of people considering the effect of rotations on these 10 to the 8 halos that should produce a direct collapse black hole. And rotation in other contexts has the habit of providing fragmentation. So it would certainly be nice to check what it does. The growth from POP3 seeds seem less favored. Unless you have super Eddington. There has been a contribution showing that it could work well, but it has been questioned whether the mini halos early on would support super Eddington. So the one note of caution is that in this context, when you're looking at redshift 6 quasars that we know exist, you're looking at a handful per cubic gigaparsec. So these are extremely rare objects. So extremely unlikely or finely tuned processes might actually be what you need. Because if it was too easy to form them, you would make too many. So I'm not really worried about, I'm more worried about being able to make them than overproducing them. So how do we tell these models apart? It would be nice, for instance, if we could detect a 200 solar mass black hole. That would be easy. You see a 200 solar mass black hole at 25, or a 300, and you track them as they increase in mass. It might tell you that the seeds are the way to go. On the other hand, if the smallest you can detect are already bigger than the ones you would do from direct collapse, you can't tell the difference. So perhaps environment is actually the solution. It would be nice to see if this idea that you cannot do it with a smooth Lyman-Werner background, but you need a nearby bright object, if that's really the answer, it would be nice to simulate whether that nearby object has time to merge generally before you get to 6 or 7, because if it doesn't, using JWST coronagraphy, you might be able to see these guys who kept the halo from forming mini halos next to each quasar or to a fraction of quasars. If the issue is also how far they have to go. If they go much less, if they need to be much closer than a kiloparsec, then it would start to be a problem seeing them well with JWST coronagraphy. But I think this is perhaps worth looking at. Especially if some of you want to write a JWST proposal, it would be nice to do the calculation first. So early galaxies not necessarily primordial. One number that I think is useful to give is that I believe that 10⁻³ solar from UV oxygen lines is more or less the reasonable limit, the smallest metallicity that you are going to measure. This is for a 5 nanojansky source with JWST. So is this enough? I'm not sure. We have seen that once you have dust cooling in a mini halo, things is not clear. I used to believe that 10⁻³ was a nice dividing line. That is, if you are above 10⁻³, you live in a world that is driven by metals, and if you are below, you are morally primordial. Now I'm not so sure anymore. So it is obviously we'll never be able to measure 0 convincingly, but is 10⁻³ or less an interesting limit? Things like CR7 would be very easy to get in spectroscopy with decent signal to noise on the continuum, let alone the lines. JWST has the potential to extend all the regular things we do with Hubble. And one thing that I'd like to remind everyone is that we designed JWST to find a 1 solar mass per year star formation for 1 million years, which was the simple man idea of forming a globular cluster. So can we detect globular cluster formation at high redshift? There are some people who worked on this. I think it's still an interesting problem. So for the sake of time, I won't say the conclusion since I was saying them as we went, but resolving power may be a limiting factor for more local abundance patterns. And I think I went. I'll skip the conferences, I'll skip the tools that we are about to release, and I'll focus on this. This is the timeline. There will be, in December, a call for the early release science. The early release science is going to be an opportunity for the community to propose observations that will go in the public domain. It's not a cycle zero call. People who win it will be asked to release products and data and help the community understand JWST. And they will be, call for proposal for that is going to be in April, and the deadline will be in August, after we know what the GTOs are going to do. And then there will be, in November 17, the call for proposal will deadline in February 18. So things are really approaching the time when you have to start writing proposals. Thank you.
Yes.
Massimo, for the search for high redshift pair instability supernovae, we may not need a dedicated survey. We may just be able to do it archival because of the redshifting, right, long intrinsic durations. We may not have to have a rapid repeat multi-epoch search. If we have a clear signature to pick them out, then we may just basically look at every single field that JWST takes for whatever purpose. And then of course we would achieve a pretty wide field coverage.
Yeah, maybe. I would still prefer W first.
Other questions or comments, or are you all starting to write your proposals?
Can you elaborate on the spectroscopy capability of NearSpec or NearCam for the high redshift galaxies, and in particular for the absorption lines?
So a very simple rule of thumb is that everything that Spitzer can see, JWST can take a high signal to noise spectrum of. And almost everything, or everything that Hubble can see, JWST can take a spectrum of. At the very faint limit with HST, getting good signal to noise on the continuum may be hard, but lines are much easier. So I think things that people talk about, like the GRB redshift 8 or the CR7 and so on, are going to be very easy to see with JWST. If we could go back to the sensitivity slide. I think at higher resolving power, the slide was giving line flux. So, is this dead? No, maybe it's dead. But anyway, you see NearSpec, and so it can get kind of a couple times 10 minus 18 in 3 hours at signal to noise 10. If it's in a, once you start to go to 3,000, the reason we didn't go to 10,000 was that JWST doesn't win over a large ground-based telescope. The higher the resolving power, the less you gain by being in a place with a very dark sky. So at 3,000, depending on what you want and where you want it, the ELT would be better. But if you are in a spot with, with a nice big OH line, then this is going to be better. And if you want an interrupted spectral coverage, or you want to do absorption lines, then probably this is better. So in terms of medium resolution spectroscopy with JWST and the ELTs, one will win for certain signs and the other will win for other signs.
What is the typical correction factor for the fact that the galaxies are not point sources?
You get, the slit is 0.2 arc seconds. Some of these objects are about that size, so you catch most of the light. You're talking factor 2, not a factor 10. For the really small ones that we see at high redshift. Of course, the fact that this guy has the micro shutters, you could imagine, in fact I plan to do it with my GTO time, you can imagine for a lensing cluster, you see an arc and you open slits tracing that arc, which is something quite nice. So studies of lensed objects in clusters, I think, will come out very nicely with JWST.
Any other comments or questions? So, well, with that, we'll take a break and thank Massimo again for a nice talk.